Occupied resources in a system with resource sharing between service-based customers. Abstract. This paper presents analytical and generalized expressions of the amounts of occupied resources in a system providing several services to its customers. This system can be assimilated to a multi-service queue. We considered that the required amount of resources for each service are deterministic, then random variables amount of resources is studied in second part. Analysis carried out on the resource occupations have made possible the dimensioning of the total amount of necessary resources that must be deployed on the queue server. They are to serve the customers up to a certain quality of service in terms of the probability of congestion. Reported to a single service case, we found from the analytical expressions established in this work the probability of congestion in the Fry-Molina traffic model. The obtained results are compared to digital simulations of case studies similar to a real system. Keywords: queuing, dimensioning, multi-service, resource occupation, resource sharing. Introduction. The dimensioning of the amount of resources necessary for a system guaranteeing a certain quality of service began in the era of Erlang 1. He established a famous Erlang B formula to determine the number required channels for a telephone network 1-2. This formula only considers a single service, voice service, provided by a system, telephone network, to users who request it. Its formula is derived from the study of a finite capacity m/m/n/nq. The results of his studies have been developed and extended by many researchers like Palm 3, Volat and Chavo 4, Joyce 5, Iverson 6 and many others. Then Iverson 7 studied the case of a multi-service system by evaluating the congestion rate of such a system with access control. Elastic traffic cases have been developed on multi-service queuing systems by Toky et al. 8-9. In 8, they proposed a multi-service queue model with SDFIFO, state-dependent FIFO, discipline. This system allocates its resources to each class of service in a balanced fairness way. They further proposed a generalization of multi-service queues used in elastic traffic 10. Other studies on a fairness resource sharing have been put forward by Bonald et al. 11, where all the resources are available to all service classes and to all the users who present themselves in front of the server. An extension of Haddad and Mazumdar 12 assesses a certain congestion in such a system. Hanchowski et al. 13 have proposed another type of discipline called CFIFO, continuous FIFO, for the multi-service queue. They approximated the convolutional model of a CFIFO multi-service queuing system while allowing variable rate based on the amounts of unused resources in the server. In all these literatures, whether it is in the sharing of resources available to all the customers present in the system, or either with variable rate, or elastic traffic, the problem arises on the total amount of resources that the multi-service server queue has for its customers. This article proposes a generalization of a multi-service queue, with fixed or random amount of resources required for each service class, in order to determine the capacity required in the server to provide a certain quality of service. Our study is based on the analytical determinations of resource occupations in such a generalized system. It is also an extension of the work done in 14 and 15. 2. Model description. Let be a system sharing its resources through customers requesting services. Each customer can request a service requiring a fixed resource from the system for a random average duration. The arrival rate of customers requesting service from the system is described by a Poisson process of intensity. IR by denoting by n the total number of services that the system can provide to his customers, assuming that the arrivals of customers of each service are independent. We can say that the arrival to the system forms a Poisson process whose intensity is expressed by the rate of customers requesting service is equal to for each I. These two expressions derive from the superposition property of independent Poisson processes. 16. 11. NNII equals IP / IP equals. Let be the distribution of the service duration requested by a customer. It is a strictly positive real random variable with mean. The duration of service requested by any customer will be denoted by S. From the total probability formula, we can express that the cumulative distribution function of S is equal to, where is the cumulative distribution function of? We will denote by its complementary cumulative distribution function. Is SFs 1, INSISIFSPFS equals ISFS is CSFS. The system is then equivalent to a queue, with a single server with a total of R resources. Customers arrive at this queue according to a Poisson process of intensity. The service duration of any customer is a random variable S with an average. These customers will use an amount of resources from the queue server depending on the type I of service requested. If customers are being served by the system, using resources are the sum of all the amounts of resources used by these customers. Another arriving customer wanting to use an amount of resources less than or equal to will be served immediately. If the amount of resources requested by the arriving customer is greater than, then it will be queued waiting for a served customer to complete and release resources. IR. RR. If the initial amount R of resources available in the server is infinite, there is a queue, in terms of customers. Customers who arrive will be immediately served. M/GI/. 3 analytical expressions. A sharing of infinite resources. We will express the total amount of resources used by the customers described in paragraph 2. Note by the probability that the system serve n customers. N. Theorem. Follows a Poisson distribution with parameter, i.e., 0.CSFSDS plus. Proof. Let be the number of customers being served at instant t, assuming that, and the probability that the system serves n customers at instant t. Nt. On the one hand, we denote by the process of customer arrivals to the queue, and their arrival times, i.e. the instance of the process. Conditionally on the counting measure of the process, the random variables are arranged in ascending order, and uniformly over the interval. On the other hand, the probability that a customer will have a service duration greater than s is. Then, the probability that a customer arriving uniformly between the interval and still being served at time t is equal to 0, TTA. Conditionally on, the number of customers still served at time t is therefore equal to n with the probability, tam equals b sharing of finite resources. For the case of finite resources, it is obvious to think of a m/gi/cq where c denotes a certain finite capacity of the system. But the analytical resolution of this queue is still an open problem, and the solutions proposed so far are only approximations 17, 18, 19. In addition, in our case, we have a variable capacity depending on the customers served by the system and their requirements in terms of amount of resources, so this will further worsen the complexity of our problem. In our research, we focus on dimensioning the amount of required resources to satisfy customers in their uses of the services provided by the system. Being given that the system has a capacity C in terms of total amount of available resources it can allocate to customers. If the requirement of the next customer is greater than the amount of available resources in the system, we can say that there is a blocking phenomenon. Two scenarios can arise: either the customer in question is rejected, or it is put on hold. In both these cases, the capacity in terms of amount of resources is insufficient. On the one hand, if we are going to deploy a lot of resources, some of them may not be used. It is therefore a waste of resources. In some cases, the availability of resources is chargeable and it will therefore be a loss in terms of investment. On the other hand, the deployment of few resources can lose some customers as we described in the previous blocking phenomenon. It is therefore necessary to determine the right total amount of resources to put in place. For this, a certain tolerance threshold must be adopted such that the probability of rejection or of placing customers on hold is less than this tolerance. Let's assume that we have deployed an infinite amount of resources. For this, the probability of using an amount of at most R resources is given by equation 5, recalled below. We can say that this is the probability of blocking the system of capacity C because since from this amount of resources C, it can no longer serve more customers. It will be called probability of congestion. For dimensioning with a tolerance, the objective is therefore to determine a capacity C such that see what happens in case of single service system and unit resource for each customer. In this part, we will see the case of a system offering a single service in which each served customer uses only a single amount of resource. For the case of exponential service duration with mean, we will see that from equations 5 and 6, we end up with the BCH, busy calls held, traffic model of Fry-Molina 2021-22. 1/ The number of services provided by the system is then. The customer arrival rate follows a Poisson process of intensity. Since the service duration is exponential, the cumulative distribution function of the random variable s of service duration is given by the rate of customers requesting service 1 is therefore 1n equals. We note that this model, which is an alternative to the Erlang B formula 1-2, is used in certain dimensioning of telephony in North America. It is observed that this model reflects much more the reality of observed traffics compared to the Erlang model 2324. Degeneralization for random amounts of resources requested by customers. This time, we consider that the amounts of resources requested by service I customers are no longer deterministic as in the previous paragraphs. Let's assume that the service I customers request a random amount of resource following a probability distribution with mean. We will denote by the cumulative distribution function of the amount of resources requested by a customer using service IIL. IJERT. We still assume an infinite amount of resources available from the system server. According to the methodology that we adopt in paragraph 3.1, to determine the cumulative distribution function of the resources occupation of the system, it is necessary to determine a CDF conditional on k customers served by the system. PRR. KPRR. We decompose this number k of served customers into the number of customers per service such as. We can have possible combinations of these customers. For each customer, the probability that he uses an amount of resource less than or equal to x is equal to if he requested service I, or with a probability of, in other words. IC. Fig 2b. CDF of the amount of occupied resources for an infinite capacity, zoomed in. It is obvious from figure 2 that the deployment of more than 20 resources does not influence the system. We deduce that the probability that the amount of occupied resources is greater than or equal to 20 is very small, close to 0. It is therefore not necessary to provide more than 20 resources to the system since not all of them will be used. From these curves and equation 6, we can conclude a probability of congestion of 10% when the system has 11 resources, and this probability becomes 1% with 17 resources. We used MATLAB, Simulink to simulate these two values of total amount of resources to verify these congestion probabilities. Model presented in figure 3 has been used. The customers, users, are generated from the user of service I blocks following a respective rate described above. Figure 3. Resource sharing model for a system having 4 service classes for its users. The probability of congestion is calculated from the percentage of time during which the amount of occupied resources equals to the capacity of the system. We then use the parameter NB used resources in the below algorithm to determine this percentage. Count equals 0. Capacity equals 11. T equals 0:0.01:2000. NB used resources resampled equals resample, NB used resources T, ZO. Used res RSMPL equals NB used resources resampled. Data. Time res RSMPL Y equals size, used res RSMPL. For I equals 1 time res RSMPL. If used res RSMPL, I1, equals capacity. Count equals count plus 1. End. P congestion equals count slash time res RSMPL. DISP, capacity equals 11. Frinf, the percentage of time the capacity is reached, percent 0.3 G backslash N, P congestion. We found the following percentages for a capacity of 11 resources, and for a capacity of 17 resources at 5,000 simulation time units. Capacity equals 11. The percentage of time the capacity is reached, 0.1073. Capacity equals 17. The percentage of time the capacity is reached, 0.0166. These are the probabilities that any user, arriving at a random moment, will find all the resources occupied. We then found the theoretical results of our model explained by the curves of figures 2a and 2b, which are respectively 10% and 1% for capacities 11 and 17. These results validate the model thus established. As a concrete example, the model can be used for the dimensioning of codes, resources, of a third-generation mobile communication network, 3G network, which share these codes through its customers 2526. This type of network provides multiple services, such as. These results remain valid for the case of non-discrete resources. In this case, the amount of resources initially available in the system is a strictly positive real number. The amounts of resources necessary for each service I can also be strictly positive real numbers, not necessarily a non-zero natural number. The random variable designating the total amount of resources occupied by the customers is then a positive real random variable. And the expressions of equations 5 and 6 are already carried with the cumulative distribution functions which characterize the real random variables. V conclusion. A multi-service system shares its resources through its customers according to each customer's requirements for each service requested. They arrive on this system according to Poisson processes characteristic of each service class. The system is assimilated with a multi-service M/GI/CQ in terms of the number of customers. Two cases of capacities in terms of amount of resources were considered, the infinite case which allowed us to evaluate the distribution of occupancy of the Q resources, and the finite case from which we derived a probability of congestion from the infinite case. The analytical expressions established have made it possible for us to dimension the system by determining the amount of resources necessary for the server with an admissible probability of congestion. From the theoretical result and the case study presented, we found that it is quite possible to determine this necessary amount since from a certain value of the capacity, the characteristic of the system in terms of the number of occupied resources does not show much variation. We have shown that the result of the Fry-Molina model is found from our model and from our result in the single service case.